Here's the last theorem in this chapter, chapter 14 on cosets, and it says that if you have a group, any group that's cyclic, that's important, and the order of the group is n, then for any, or for all, for any divisor, any common factor, any factor of that group, of the order of the group, any factor of n, then there is only one subgroup of that size, d. So, putting it another way, for each divisor of n, where n is the order of your group, cyclic group, okay, then for each divisor, there's only one subgroup of that size, d. Okay, and so this theorem is proving that. And typically, when you're trying to prove uniqueness, like proving that there's only one way something can happen, the typical way to, the strategy of the proof of that is that you assume that there's a second example with the same properties, and then you prove that those two are in fact the same thing, and hence there's just one. Right? So let's try to prove that any subgroup of a cyclic group that has the size d, where d is a factor or a divisor of n, right? But there's only one group. Well, firstly, let's find the group. Now, G is of this form, right? Because you're told that it's cyclic. So your A here would be your generator, let's say. So here's your group of size n, right? 1, 2, 3, n. So it has n elements, and A is your generator, right? So if we take a subset of these to create a new group, a subgroup, it'll be of this form. Now, there was a theorem that any subgroup that we did a while back, if you take any subgroup of a cyclic group is itself cyclic. The subgroup is cyclic. That was one of the proofs we did. So a subgroup H will be of this form. Now, we can show now D divides n. All right. So let the quotient, the result of the division, let it be t. Okay? So we'll just say let t be n over d. It's the result that you get when you divide the order of the group by this divisor. You get t. So you can form a subgroup. It will also be cyclic. That's a theorem we did earlier. To this power, a to the t, a to the 2t, a to the d minus 1 times t. Now you can see this is a subgroup of this, because this t would be here somewhere, and 2t be somewhere else further along. Right? Now, how many elements here? Well, you've got that one, that gives you d minus 1 of them, plus one more, so you get d. So the order of your H here is d. Right? So you have got yourself a subgroup of order d. Right? There it is. Okay, so we have the existence, we've shown the existence of a subgroup of order d. We have at least one of them. So let's assume that there's a second one, and then prove that second one, now let's call it k. So the second one, we'll just call it subgroup k. It's also a subgroup of G, and it has the same size, right? So the order of subgroup K is also D, right? And then given that, we will prove that in fact that K is the same as H. That K equals H, and that way we proved uniqueness, right? Okay, so this is what we have to prove. That K, this second subgroup that we propose exists, that it actually equals H, and therefore there cannot be a second one. Alright, so let's go about the proof. So we assume this second subgroup exists, K. Let B, just any element of K, so let's assume that B belongs to K. Now, if that's the case, now K is a subgroup of G, right? By definition. So therefore, the form of B must be of the form of A to some power, right? So K is a subgroup of this, hence a subset of that. So any element of K must be of this form, A to some integer, right? Has to be, because K is a subset of G, and therefore all the elements of K must be of this form, A to some power. So B is of this form, some integer s. We don't really care what it is. Now let's see. So now from theorem 51, here you need a reminder. So you take any element of a group G, and the order of that group is n. Then that element raised to the nth power will be equal to E. Remember that? I did that in the previous session. Okay. Now let's use that now. So that means that B to the D is E. Now why is that? B is any element of K. Right? K is a subgroup, so it's a group, right? Still a group. And what's its order? What's the order of that group? Well, D. So any element, here it's X, here it's B. The order of your group is N. Here the order of the group, which is actually subgroup, K, is D, right? So any element of K raised to the power, the order of K, by this theorem, is equal to E, right? Using theorem. So B to the D is equal to E, right? But B is of this form, A to the S. So plug in, substitute for B here, plug in A to the S. So you get A to the S to the power D equals E, right? So you can rewrite that as this, right? So A to the SD is E. Now I go way back, theorem 17, long time ago. It's on page 44 of the textbook, if you have it. There's a theorem that says if A to some power equals E, and then this theorem says that the order of your group, the order of this, divides this. Right? That was the theorem. Okay, so that means you can. So if n is a factor, same thing. If n is a factor of this SD, and that's what theorem 17 says, then you can rewrite this SD as some multiple, some integer times n. Right? So if n is a factor of that, if n divides that, you can write SD in this form. So SD is of the form mn. Alright, so we can then solve for S. Just bring the D, take the D under. So if SD is mn, then S is just mn divided by D. Okay. Now B is of the form A to the S. That's here. Right. B is of that form. Oh, wait a minute. Just a minute. I made a mistake here, just damn. Let me check. Should be there, mate. Should be there. Right. Does that make sense? Now B is A to the S. Here it is here. And S is here, Mn over D, Mn over D. Okay, now that's correct. Now, N over D was T, right? N over D is T. So this is of the form A to the Tn, A to the Tn. Now look, have a look at this. These terms here